So as you answered the questions near the bottom of the first page, I asked you to examine where x equals 1 and where x equals 2, the two places where this function f of x is discontinuous. You noticed, when you're comparing the limit from the left and the limit from the right and the actual limit at that value, started to see what's going on here. So this function is discontinuous at x equals 1. Notice here I approached from the left, I was headed toward y equals 0. I approached from the right, I was approaching y equals 1. The limit doesn't exist because the limit from the left and the limit from the right are not equal. That's from section 2.1. So the limit didn't exist. That might be a key to my problem. Here, for when x equals 2, my limit existed. As I approach x equals 2 from the left, I'm approaching the y value of 1. As I'm approaching from the right, I'm still approaching that same spot, that y value of 1. But this time, what gives me a problem? The reason I have a hole, I was approaching the same space from the left and the right, but somebody filled in the wrong dot up there. So here the limit from the left did equal the limit from the right, but those limits were not equal to the actual function value. So ladies and gentlemen, this is the definition for continuity at a point. You can see there's a place for you to fill in at the top of page 2. A function f of x is continuous at an x value at x equals c if the limit of f of x as x approaches c is equal to the actual function value, so f of c. So it's subtle, but notice what that implies. If the limit as x approaches c of f of x is going to equal the function value, that means that limit must exist. So if the limit exists, that means the limit from the left had to equal the limit from the right. So you could also think of it like this. A function f of x is continuous at x equals c if the limit of f of x as x approaches c from the right equals the limit of f of x as x approaches c from the left, and that is equal to the actual function value f of c. So we'll do two examples. This is how you might see this problem show up in the AP test. I have a piecewise function with two pieces. They're both linear pieces, and one piece of the function is good for x values less than or equal to 2, and one piece is good for x values greater than 2. And here I've been asked to choose c, so c sort of the slope of this bottom piece of the piecewise function, so that my function f of x is continuous. So I could make a picture. I've made a picture for you here. Your picture. There we go. So this is the top piece of the piecewise function. What ended up as a blue squiggly. It's supposed to be a blue line. And I know the y-intercept of my second piece is supposed to be 6. So I've graphed 6 up there. And I try to draw it in with the right slope so that these two pieces of the piecewise function would actually touch at x equals 2. So I can come through and erase this. That's the piece that... So I have to pick c right, so I have to pick the slope of this green line so that my two functions touch. There are two pieces of the function touch. So how do I do that? I'm going to use the definition of continuity at a point. For a function to be continuous at a point x equals c, in this case the c is the point where the two functions change over, where they change who's in charge. So in this case it's x equals 2 if the limit from the left of f of x equals the limit from the right of f of x, which is equal to the actual function value. In this case, we would call that f of 2. So the top piece, x plus 3, that's going to be the limit from the left. As I come along my function from the left, I'm following this piece. I'm following this piece. So the limit from the left is the limit I would get if I plugged in 2 for x here. So I'm going to set x plus 3, when x equals 2, equal to the limit from the right, which is whatever cx plus 6 is, when x equals 2. And that all has to equal the function value. In this case, look at the domain of your function, the two pieces. Which piece got the underline? So if you actually tried to plug in 2, which rule would you use? It's the top rule. I'm going to plug in 2 for x plus 3, and that result is 5. So the limit from the left has to equal the limit from the right, has to equal the limit of the actual function value. So I have a three-part equation here. X plus 3 when x equals 2 is also equal to 5. So really all this means is that 5 has to equal cx plus 6 when I plug in 2 for x. So I can write this equation 2c plus 6 equals 5. I can solve for c and find out that the missing value c in this case is negative 1/2. And you can see that green line that I drew in, what was its slope? Negative 1/2.